Hello and welcome to my first YouTube video about Kaggling. My name is Henning and I intend this screencast to be something like watch as I go video series. As you can see, I'm not like the top Kaggler, or I'm not doing Kaggle a lot, but I joined recently. Well, actually I joined a year ago, but I started recently doing some competitions and I found it to be a lot of fun, and I think I have some things to share for people who are maybe just starting out doing Kaggle or don't have so much experience with Python. But I also hope that I can grow and learn a lot myself while I'm doing this. So I will briefly explain what kind of setup I will be using, and after that I will just get started with the CrowdFlower competition. So first off, I'm using the Continuum Analytics Anaconda distribution, so you can download it here. I will actually be using Python 3 because I'm not I never used Python 3 a lot, so I thought it might be a good way to teach myself the differences to Python 2. And yeah, basically I have an empty system right now. I just installed the Anaconda distribution and I downloaded the Kaggle data, and as you can see I already did a few other videos and tried. This is my fourth recording, I think. So we're gonna do the search relevancy prediction competition. The goal here is given a query and an item title and item description, predict how human evaluators would rank this query on a scale from 1 to 4, where 4 is the best grade and 1 is the worst grade. Let's just take a look at the data page. So this seems to be the setup they labeled their data with. So the user sees a query and then the product title and actually an image, and then the user is asked to say, oh no, it's off topic, it's acceptable, good, or excellent. Yeah, that's probably everything about the data. So maybe we just get started. So for notebook, for all my Kaggle competitions, I actually use the IPython notebook. So once you install the Anaconda distribution, this will be installed by default. Make sure to actually run conda update IPython, I suppose, to get the newest version of the notebook, because I think when I downloaded Anaconda it actually had an older version, and as you can see I immediately get an update. So this might take a little bit. Let's close this again. So I already started in that competition earlier, but then I was busy at work and didn't have a lot of time. Hello, internet? Ah, yeah. Let's see where I'm at. Place 85. Let's definitely beat that. Okay, let's get started. So if you type IPython notebook, it will usually open up the notebook in your browser, and then let's just make a new notebook. And name it CrowdFlower. So the first thing I actually always do for every competition is import pandas as pan spd and import numpy as np. And then let's immediately read CSV. So, and then we want train CSV. And actually, let me immediately say that the index column will be our ID column. So for those of you who don't know pandas, pandas is basically a wrapper around NumPy with some really nice functions to operate on NumPy arrays. And the data frame always has an index and a column field. Let me just maybe show it to you. So this will be our train data. Oh no, mangled up. So local train data frame train head. So for example, you can execute a command head on this data frame and it will show you basically like the head command in Unix what data you have. And as you can see, my column fields are in this case query, product title, product description, median relevance, and relevance variance. And then I set the ID should be the index, which means I can access the rows by using the ID. And I guess they are just numbered from 1 to however many we have. One thing we can immediately see is that we will have NaN values, and also the product description contains weird characters. I think it's not just like carriage return characters, but also the HTML and everything will just be in this description. And the relevance variance is actually, they asked like 3 or 4 people per query, and then they took the median relevance and then the variance of that. So this variance is explained by having like 3 or 4 people rate this query. So in order to get a better insight on the product description, let's just check. So actually quite a few of them are none. And yeah, so in order to deal with that later, I will just fill them with an empty value. And in pandas, you can do that by saying fill NA and then empty string. So if I reload that, then you can see that suddenly it's just an empty value. So with pandas, you can actually make a lot of nice queries. So I can say group by query and then describe. Describe is similar to R, I suppose, although it has less information, I think. So it will just generate you can see the count, mean, standard deviation, and information about those groups. And if you have numerical values, it will skip all string values and just use the numerical values to generate these statistics. So we can see the acoustic guitar clamp appears 30 times and the mean rating is 2.8. The mean rating actually is 2.8. Whereas here in Adidas fragrance you can see 3.6, so probably many of them or most of them are actually 4. But as type, I believe if we do as type string, so with this converts all the columns into strings. Oh, also the numerical columns as strings. If I now describe it, it should actually do unique counts for me. So yeah, now you can see it looks different. Now we have count and unique and top and frequency. So on these, out of these 64 median relevancy entries that we have for this given query, the top one, we have 4 unique values. This means all of them appear, like 1, 2, 3, 4. The top one is 4 and it appears 57 times, so almost all of them are 4. Here you can see the empty product description is the most frequent one. Appears 17 times. And this is the most frequent title, appears 2 times. So here we can see unique is only 3. This means one of the values is missing. With pandas you can also make really easy plots. For example, let's try to plot the median relevancy as a histogram. Histo, I believe is the command. Just hist. It takes a while. Don't have the most powerful machine. Oops. Okay. In order to plot inside the IPython notebook, you actually need to plot line. Let's just execute both of them again. So now we can see a histogram of the ratings. You see, we barely have 1,001 ratings, but we have about 6,004 ratings, which means that these search results probably come from a good search engine. Yeah, let's immediately get started. In order to predict text, so let's head. In order to predict text, we need to put the text in some form that we can do machine learning on it. So what you usually do is some form of pre-processing, and then you do something like a bag-of-word approach. I'm gonna explain all of those steps, and later on we will use scikit-learn's transformations for that, but just so we understand what happens underneath. I want to give a brief overview on how you can approach it. So usually to create the bag-of-word vectors, you take every word as a feature. So if you have done other competitions, you might know features like, say, predicting the prices of apartments or something. Then you could have a feature like the size of the apartment and the number of rooms, and if it has parking or not. And then you would have some features here like, say, 35 square meters for Tokyo. It's already kind of big and expensive. Number of rooms will be 1. Parking, no. And then you get some label, which will be your price, which can be, say, $850. And so you would do prediction like this in different competitions. So what you do for words is you just take every word as a feature and make it a sparse vector. So if we just had this bridal shower decorations, bridal would be a feature, shower would be a feature, and decorations would be a feature. And then in our case, bridal appears, shower appears, decorations appears, and our prediction label would be 1 for this given query. I mean, usually you would use the query and the product title, but just to show you. So the second element would have no bridal, no shower, and no decoration. So in this case, our vocabulary is useless for our second query because none of the words appear. In case that was confusing, let's just implement it in code, and it might be a bit easier to see. So what we first will build is our vocabulary, which I will build as a dictionary and word to index. So the index will be the position in our feature vector where the word will appear. So let's just build the dictionary from the queries at first. For query in train queries values actually gives you the underlying NumPy array of this particular column. So print query should just give me the first query since we are in Python 3. Yeah, bridal shower decorations. So what we want to do next is say forward in query dot split on spaces print word with brackets bridal shower decorations. So we want to store the word in our word dictionary, and it should be only unique words. So we will have word to index word equals length of word to index. So the first word we input here will be mapping to the index 0, the second word to index 1, the third word to index 2, and so on and so on. And since it's a dictionary, all the words will be unique. One thing that we need to take care of, though, is that we say if not word in. Otherwise, if a word appears multiple times, we would override the first index with the later occurrences, which we don't want to do. So let's just calculate that and look at how it would look for our first vector. So you see bridal would be at at the position 0 in our feature vector, and decorations position 2, shower position 1. And now we run that. We have a bunch of different words and the position they will appear in. Yeah, we can immediately build a word count. Yeah, let's immediately build a word to count dictionary. Let's just make this a default dict. So Python default dictionary makes it easier to count stuff. For example, I will explain in a second. So from collections, import default dict. I really have to install my Vim bindings here. Word to count, actually here. So in a regular dictionary, if you would do something like this, plus equals 1, this one would fail if there's no entry for word already. So let's just do it. So now it says key error because we tried to increment the key bridle by 1. So it goes to the regular dictionary and sees is there an entry for key, but there's no entry for key, so we cannot increment anything. And then it gives you a key error. But if you use a default dictionary, then it will, by default, if the key is not present in the dictionary, always return an integer, and the kind of empty integer is 0. So this will start counting from 0. Let's just check our word to count. So as you can see, the word pans appears 55 times, poster 23 times, converse 57 times. So this would give us, actually, we can check our vocabulary. Right now we only check single words, right? Later we will do bigrams and trigrams, but for now we just have single words. So we have 493 words in our vocabulary now. Let's just look at the highest counting words, for example. So for key value in word to count, we actually want sorted word to count items. So this items returns all key value pairs of a dictionary. Key equals lambda x. X1 will be the values in this case, and the values are our counts, and I want to sort the highest values first. Print key value. Oh, print Python 3. Okay, let's stop it. So, oops. So we can see the word dress appears most often in our queries, and then it's coffee and maker, shoes, case, for, memory, bike, woman, candle, men's, pants, mouse, blah blah, jeans. And later on we will filter words like and for because they carry no meaning. So I don't know, if someone types a query shoes and pants or something, and you return an item that just contains and as the item title, then it's not very helpful to the user. So we don't want to match and to any queries. I think in the description there might not be many of those stop words, but especially in the title, but especially in the description we will have a lot. Charger, KitchenAid, blah blah. So let's do, say, if smaller 100 break, because now I want to show you what happens if we take the product description and how dirty it is. So let's create the same vector for the product description and then print out the most common words, and you see the counts change quite a bit. So and is now the most common word in our corpus, and the and spaces and a and 2 of with 4 is that's all useless words, like your in the doesn't help us at all. So how do you usually clean them? There's already many stop word lists, for example from scikit-learn or NLTK, and we will use both of them actually. One thing that you can see is that upper and lower case is right now also a different feature, and we probably want to combine them. So one thing that we can immediately do is say we take the lowercase queries, and now there's only one len. Let's actually print the length of the word to count to see how many words do we save from lowercasing, like how many less features do we have. So now we have 69,000 features. So 9,000 features just go away by lowercasing. And then let's just check another thing. So from sklearn, sklearn, and I think it's pre-processing text. Feature extraction. I always confuse where to find it. Feature extraction text, English stop words. From scikit-learn text import English stop words. So if word in English stop words continue. So now we skip the stop words, we can actually print them. So skipping former word, skipping with, a, of, with, and less between, all like pretty useless words. That's one disadvantage of the IPython notebook. If you print a really long list, it will make your browser super slow. So we stop printing with my browser. Yeah, current output takes a little bit now. Sorry for that. Never print like too long lists. Need to re-execute that without the print statement to remove it. And suddenly everything is nice again. Okay, let's see. 60,600. It only removed like 200 words or something, but nevertheless, we still have punctuations and spaces, so we can probably, if not word.strip and or so if not word.strip, word strip removes the spaces at the front and at the end of the word. Since we split at spaces, it will be at most one space in the word. So actually word strip will make it the empty string, and if not, word will just skip it if it's empty. Then let's see what else we have. It's already quite alright. Let's check. Since we want to build the vocabulary, if you want to select more than one column in pandas, you have to make double columns. Let's just actually go for query and product title and just leave the description out for now. We will have to do some additional cleaning for that later. So product title, numpy array has no lower query, comma, title. Now we get two return values, and 3 plus Actually, I will now join the title and the query into one sentence. Join query title query. So this one will just concatenate query and title with a space. And now let's see, we get about 14,000 words now, that's okay. Black dress, woman's. As you can see, woman and woman's will be a different word in our text. I was just thinking how probably also later on man and man's. So maybe let's just build a feature vector from that, and then we will just do some similarity between vectors, and afterwards we will start improving on our preprocessing and figure out whether we actually get better or not. So now that we have the word to count vector, we can actually start saying making us a NumPy array which will contain our features. The NumPy array will contain our sparse vectors, so we need a NumPy array of shape, length, actually data frame, our data frame has a shape attribute which gives us the dimensions, and the first dimension is the number of rows, so the number of queries we have, number of training examples, and this one will be the length of word to index. Data type not understood. Do I have to pass it as an array? Yes. So we have 10,000 training examples and 14,000 features. So features. What we do now is let me think. We should probably take let's just convert all our queries and this will be the query features, and this will be the title features. So let's go for all. Actually, this will be the same loop as up here. This time we won't join them, we will just convert them into a feature vector. So, oops. And thinking about it now, we should make that a sparse array. I will show you how to do that later. For now, let's just keep it in memory because it's not too big yet. So for word in query split, this time we don't combine train and query, we will process them individually. And I actually need the count. Or let's call it index, it's easier. Is index a built-in? I'm not sure. Enumerate. I need to install them bindings here, it's crazy. So now we will take our query features, query features, did I not execute this yet? Query features index, this is basically the row, let's call it row index, make it easier to understand, row index, or the ID if you so want to. This gives us one array of length word to index, and we actually index word to index word. So this will become 1. We could also just set the word count there to say this feature is present. Let's just make it binary for now. Words appear or they don't appear. And we actually do the same thing for title split, title features, row index, vector index, execute. The NumPy int46 object does not support assignment. Why not? What's happening? Print. Oh. Wait. Query feature. Oh, ooh, ouch. Ouch. Oops, 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 oops. Oh man. Yeah, we need to, if we say NumPy array and we give it this list, it will just make a list with two values, namely these values. We actually have to say NumPy zeros to make an array of that size. And then I suppose we have to give it a shape. So actually we don't remove those brackets. Yeah, now if we query features, yeah, now we have an array with just zeros, empty matrix. And now we set a 1 for every feature that's present in our queries and titles. Accent, where? Key error, accent, row index, word to index. Word, title. Then what should appear? Query, lower, split. Accent. In the title. Debugging. Okay. Build my own yeah, so now it gets a bit messy, but we lowercased everything before we put it in there, right? And we also removed the stop words. That's of course the same thing we have to do down here. So yeah, what I see, we need to write a preprocessing function where we actually put that string and it gives us back a preprocessed string. Let's immediately do that. I thought I might start out making everything from scratch first and then refactoring into functions, but let's immediately start out. So we get a string and our preprocessing will basically filter stop words and lowercase it. So string and then we will say filter string equals list for word in string dot split if not word in if word split strip or if word strip or and not word in English stop words, filtered string and word. So this will keep the order of the words that we find, but remove all of the spam the words. So now we return space join filter string. So now we can take this and maybe we immediately return the tokens. Why should we put it back together? So this will return a list, then we can just say pre-processing query. See if it works. Seems to run. And so on seems the same. And here we just pre-processing query. This one is running. So now if we plot our query features, we can see, okay, like of course in the first feature vector we find the first 3 words. That's just exactly how we define the features. So if we take this second feature vector and how can I print this? For a print a. Everything 0. Next. I don't know. Position 20 has a single one, so this seems to be a weird query. Let's check it out. Train query. We only want to query. IX actually selects the index row, so now I can type a number and get them. So 0 would be 1, so I have to go for 3. Oops, should print it. And he's complaining about during handling both exceptions occurred. Ooh, hero 3. Why is there no 3? Nice, so they filtered some of the queries. So it should be this one. Ah yeah, it's just a one-word projector, right? So that's why our feature vector only contains one entry. So it's a 14,000 dimensional vector with only one entry. That's pretty inefficient, but we will figure out how to cope with it later. So if we now from sklearn similarities? No. What do we have? Calibration cluster. I forgot, let's just check it. Cosine similarity. So we want to compute the cosine similarity. What that essentially does is it takes two vectors and it measures the angle between them. So if the angle is 0, the distance between those vectors is 0 because they point in the same direction. Or, like, except for the sign, they could potentially, I guess, they could point in the other direction. But yeah, so if this distance gets 0, they point in the same direction, and if this distance gets 1, they are orthogonal to each other. So we get it from... Where do we get it from? L2... sklearn matrix pairwise. Matrix pairwise distances. And then import cosine similarity. Yeah, screw that up. Oh, it's just pairwise. Cosine similarity. So down here you can read that if you use the sparse matrices and actually the TF-IDF vectors, you can just use the linear kernel to compute it. That's also something we will do later, but for now just stick with the basics. So we take our first query and our title features and our first title, and just calculate the cosine similarity. Which is 0. Let's print the label as well. So for row index, comma, label in train, median. I'm not sure if any of you actually talks to themselves while coding. I do. Print title has similarity and score and label format. So title row index has cosine similarity. Row index. Row index. Let's actually indent it somehow nicely, possible. And label bracket, and then actually bracket around here. Oops, forgot the comma. Oops. What is that all about? Median relevance. Always in this competition I write relevancy. So as you can see, like the first 0 title has a similarity of 0 and label 1, which is good, so they are not similar at all, and that's the worst label. Title 1 has a similarity of 0.5 and a label 4. Title 2 has 0.4 label 4, 0.2 label 4. So as we can also see, like sometimes the ranking is not pretty good, but the similarity is high. We will try to improve on that a little bit later. So what you can actually do right now is use... oh, it's still calculating. You could just use both feature vectors, like for the query and for the title, and then use this cosine similarity as an extra feature, which would give you about a 28-something thousand dimensional feature vector, and then you just train a logistic regression on it and try to predict those labels. But I think we're gonna do that in the next episode, because I got to go to work now. I hope it was enjoyable for some of you. If anyone watches it at all, please leave some comments. I'm also open for criticism, and if you have any improvement ideas, if you see that I'm doing something that's really stupid and could be done in a better way, please tell me. Because, as I mentioned in the beginning, I'm a beginner myself, and maybe I'm hoping that it could be a two-way conversation. So, like, I want to make this for people who are starting out, but I'm also happy to learn from people who know a lot more than I do. Yeah, I hope in the next episode we will actually do our first predictions and actually use the metric that is provided on the Kaggle page, the kappa squared metric. And then from there we will gradually improve our score until we can go higher than our current score, I think. So thank you very much.